Our last lesson in this gases unit is on some more gas stoichiometry. We have done a little bit of stoichiometry with gases before when we learned about stoichiometry in the first place, but now that we've really dived into gas behavior and how gases behave under different pressures and temperatures, we're going to maybe add a little bit more fun stuff to our stoichiometry abilities. Today, you guys know when I do stoic, I like to use my colors, my green to represent my given information and my red to represent the information that I'm trying to solve for from a stoichiometry problem. Also, you'll need your calculator and your periodic table because that's your chemistry toolbox. So let's get started on today's lesson on gas stoichiometry. What is a chemist's favorite plant? Stoichiometry. Okay, now it's very important to remember that all stoichiometry problems start with a balanced equation. The reason for this is those big numbers in the front of every single reactant or product, the coefficients are important for the mole ratio component. So let's kind of review what we've learned so far with our stoichiometry knowledge up until this point. Now keep in mind with stoichiometry, this middle step is the most important step. This is where I execute or use the mole ratio. The mole ratio is the number of moles of one substance to another in a chemical reaction as determined by those coefficients in front of those substances. So all stoichiometry, I start with information about one substance in the chemical reaction, and I'm asking you to find some information about a different substance in a chemical reaction. In essence, I must cross the dotted line, and crossing the dotted line means I need to use the mole ratio. Okay, so far we've been having some options here. I could have given you grams of your given starting substance. I could have given you moles of your starting substance, and we did a small extension of I could have given you liters of a gas at STP. Now that we are fully into this unit on gases, we understand a little bit more about STP, which is why we're going to maybe do some more things on here. But after crossing this dotted line, I can solve for grams of my ending substance. I can solve for liters of a gas at STP of my ending substance. Now the unique thing here is that if you'll notice going from liters of a gas at STP to liters of a gas at STP, if I wanted to do the full pathway, it has me multiplying by that molar volume, or dividing by that molar volume first, and then finally multiplying by that molar volume. So really the important step there is strictly the mole ratio, which once again, we will review all of this stuff as we get down into it. So now that we've learned all about the behavior of gases and our gas laws, I want to zone in on specifically Avogadro's law. What does Avogadro's law say about gases? Oh, he said something very interesting. He says if I have equal volumes of different gases, they're gonna have the same number of moles. But the conditions where that is correct is if I am at constant temperature and pressure. I've been blasting this into your head, I feel like, all unit long. If they're at the same temperature and pressure, different gases, if there's the same volume of both, they will have the same number of moles. I'm just gonna start using constant temperature and pressure as an abbreviation of CTP. I don't think that that's a super sciencey, well-known abbreviation, but it's gonna work for me, and I think it'll help you guys kind of understand on tracking your thinking process when this may apply for some stoichiometry. So here's the thing. I am saying that my moles are basically my volumes, or the ratio of my moles are the ratio of my volumes. So this is going to allow me to use the mole ratio as a volume ratio, just by what Avogadro is stating here, that equal volumes of different gases will have the same number of moles as long as we are at a constant temperature and pressure, okay? Now, this is also a review. If that temperature and pressure is specifically standard temperature and pressure, meaning at STP, 1 mole of any gas will be specifically 22.4 liters, okay? So putting this all together on my stoichiometry map, we are now kind of zoning in on not only STP, But if that temperature and pressure is just constant, it doesn't have to be standard, meaning 1 atmosphere or 273 Kelvin. It can just mean those gases are constant temperature and pressure at the same temperature and pressure, where their volumes are going to be also equivalent to the mole ratio. So we can kind of do this little bypassy step, which is really exciting and cool. So we know what to do here if I'm at constant temperature and pressure or at standard temperature and pressure when it comes to solving for the volume of a gas. But I mean, we're not always going to be at constant temperature and pressure, and we're not always going to be at standard temperature and pressure. So how does that affect my ability to solve stoichiometry problems? Well, you guys, we now know the ideal gas law. If you are not at constant temperature and pressure or standard temperature and pressure, you get to use the ideal gas law to help you out. So what this means, and there's going to be some words here, and let me just talk through them. We're going to map it out here together underneath the document camera here in a second. But if you are given the volume and a pressure and temperature that are not CTP or STP, you just use this ideal gas law to solve for moles, which moles in this equation is N. After I've solved for moles, guys, that's moles of my given. I can go back to my stoichiometry. I'm like, oh my gosh, I'm at my given moles. That means you can just jettison straight through the mole ratio and solve for whatever you need to solve for with your stoichiometry, just like normal. But what if you're asked to find the volume, but not at CTP or at STP? Well, I'm going to use stoichiometry like normal from my given side. And then I'm going to get to N moles right here. And once you're at N moles, if it's not CTP or STP, you can plug that value as N into your ideal gas law and solve for the volume from it, which is really cool and exciting, which allows us now to add another branch to our stoichiometry map. I know it's looking a little spidery. That's okay. So I just added here in the middle, if you were asked to solve for the liters, or if you were given the liters of a gas not at STP or CTP, you plug in here to solve for your given moles and then crank through here to figure out what you need to. This also applies for if you need to solve for the volume of a gas not at STP or CTP. So let's bounce down to the document camera and kind of, you have this same map here underneath or on your notes page here. But what I think helps me is, yes, we're going to be using the colors. What I think helps me is that I get to that ideal gas law, and my goal, if my given is volume, not under standard or constant temperature and pressure, my goal is to solve for N, solve for N, solve for N. Then I have my given's moles, and I can just mole ratio blast it out. Now, if I need to solve for the volume of a gas not at STP or CTP, my goal here is once I get to moles, I stop on my ending moles and I say, okay, my ending moles, I can then now pull out of the stoichiometry train track and as N and solve for V through that way. So kind of the key thinking here is on all of these guys, this section right here, in this section right here, I'm like asking myself, oh, in what way am I supposed to be solving for the volume or the liters of a gas? It's all about looking at what is your temperature and pressure telling you to do. If you are not under standard or constant conditions, here you go, ideal gas law for you. If you are at standard conditions, you can either ba-bum, 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 and anything else using your 22.4 liters is equal to 1 mole. Or if you're going strictly from volume to volume or liters to liters from your given to your ending, you can use that as the mole ratio as a volume ratio. This now also we know because of Avogadro's law doesn't only apply for just STP, but I can use that under constant temperature and pressure, okay? So I like to think about in this section down here, when I'm going from volume to volume of my gases, that mole ratio really is a volume ratio, which means instead of saying moles over moles, I can say liters over liters, right? So on these sections, for choosing, I'm going to look at T and P. Looking at what the temperature and the pressure they've provided me will let me know where I am starting in here, okay? If it is standard or CTP, I'm not using my ideal gas law. If they give me actual values that aren't standard or CTP, ideal gas law. Okay, so let's go ahead and do our first problem. Oh my goodness, and I'm gonna let you know, I gave y'all some wackadoo balancing to do on some of these problems, not because I want y'all to balance really, really hard problems. That's not the point of this lesson. The point of this lesson is to focus on the stoichiometry. So I'll probably gloss over the balancing and kind of do it really, really quickly. So don't worry too much about that. Okay, First of all, you guys, you know me, I'm gonna skip over all those words. I see an equation. I know an equation is essential for stoichiometry and it has to be balanced. It is not balanced. So let's go. Looks like I have solid sodium reacting with liquid water to create hydrogen gas and sodium hydroxide. So this is a single replacement reaction. And we know sometimes it is super beneficial for us to write water as HOH. So it looks more like a couple between hydrogen and hydroxide, right? So that way when I look here, I can see hydroxide in sodium hydroxide over here, and then the hydrogen that's outside of my hydroxide is represented over here. So that helps me with the balancing a little bit more. Specifically, it looks like, oh my gosh, you guys, I have 2 hydrogens that are not included in hydroxide and only 1 here. So I'm going to start off by putting a 2. Which then, yes, makes me have 2 hydroxides on the reactant side, which then I'm going to put a 2 in front of sodium hydroxide on the product side, which then the only thing I have to do last is put a 2 in front of my sodium. So now I'm ready to read my problem and figure out, well, what is it that they gave me here? So remember, I look at the number and the number helps me out. It looks like it says how many liters of hydrogen gas will be produced at STP if 5 grams of sodium reacts with water. So my given is grams. Guys, I'm not even really doing anything new. My given is not anything with a volume of a gas. My given is a grams of somebody else. Well, we got to find where the sodium is here. There he is. So I always like to write my given 5.00 grams underneath the of what, because that lets me know that this number up here is going to be important for me when it comes to maybe a mole ratio step coming up. Okay, so what is it they're having me solve for? How many? Oh, liters. My ears are perking up. I know if I'm solving for liters of a gas, it's gonna matter what the temperature and pressure is to figure out what my pathway is of hydrogen gas. So I'm going to go to hydrogen gas, and I'm going to say question mark liters. And now I'm going to specify, are we at CTP or STP or some other values that I've provided you with of temperature and pressure? It looks like we are at STP. So I'm going to be solving for liters of this hydrogen gas at STP, which means I will be ending down here. So we are going from grams of our given to liters of our unknown at STP. So it looks like we're gonna go boom, 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 boom. Amazing. Okay. And guys, we've been able to do problems like this before. This is actually not a brand new thing, but it is worth our reviewing time because it's been a while, I feel like. Okay, so we set up our stoichiometry. I'm gonna use my green to represent my given every single time. My given is 5.00 grams. We always specify of what, because that is important. And so we will do sodium. And if you get stuck, y'all are like, I gotta memorize this map again. You do not. Just let the units walk you through the steps of the processing to get through the problem. So I have grams of sodium here, which means I need grams of sodium down here so I can cancel them off, right? And you're like, well, what do I put in front of a grams? Well, any stoichiometry, if you're using grams, that's the molar mass of sodium, which states there is a certain amount of grams for every 1 mole of sodium, right? And you're like, okay, well, what number do I plug in there? That's where our periodic table comes in handy. We just find sodium on our periodic table, and his molar mass is that decimal number of 22.99. So I can fill in 22.99, which is oops, awesome and amazing. So I've canceled it out. Now I'm at my givens moles. That is a super important step because I'm ready to grab those numbers up at the top of the given and the unknown substances in my chemical equation and use them as the mole ratio, okay? So it looks like I have a 2-to-1 ratio for every 2 moles of sodium. I have 1 mole of hydrogen gas. I need to put the moles of sodium part on the bottom so I can cancel things off, right? So I'm gonna say 2 moles of sodium. For every, watch me switch colors because this is me going over the dotted line to talk about my final guy, my hydrogen guy. For every 1 mole of hydrogen. And the point of this, or the way I got these numbers, was the balanced chemical equation. So for the process of modeling, I'm going to circle them. So I can cancel off moles of sodium. I'm now at my ending moles, which is really exciting. Okay, now this is where the temperature and pressure came into play. We decided, or we did not decide, the problem told you, that we're at STP, which means, oh my gosh, you guys, 1 mole of every gas at STP will have a volume of 22.4. So I'll be using that molar volume as a conversion factor because the temperature and pressure is specifically standards in this case, okay? So I need moles of hydrogen down here. And the point of this step is to get to the liters of hydrogen at STP. So the molar volume states 1 mole of hydrogen will be 22.4 liters of hydrogen. This allows for me to cancel off my moles of hydrogen, and that looks good. So basically what I've done here is I've gone from grams to moles of my given, moles of my given to moles of my unknown by using the mole ratio, and then because I'm at STP, I get to use the statement that 1 mole is equal to 22.4 liters. So I'm ready to grab my calculator, and in my calculator, I'm gonna multiply everything on the top together and divide by anything on the bottom. So I have, let's see, 5 times 22.4 equals, and I have 2 things I need to divide by on the bottom. So I'm gonna say divided by 22.99. And I'm going to say divided by, 2, which is important. Okay, so this is what my calculator gives me. So now I have to round this to the appropriate number of sig figs. The sig figs are always determined by the number that they gave you in the problem, okay? So this has 3 sig figs, right? So I'm going to round my answer to 3 sig figs. 3 sig figs would be 2.44, right? I don't have much space here, but we're going to try 2.44. What are the units on this? Liters. We were solving for liters, right? And of what? H2. Guys, we've done this before, but this is a nice review. It's just we know how to navigate now through our map to figure out where we go when we're solving for volume, depending on our temperature and pressure. Okay, we have, I think, three more problems for us to work through. Now that we've kind of got the rhythm of this Stoic down, especially for the simpler problems, I'm going to maybe pick up a faster pace when it comes through some of the remaining problems. Okay. It says, what volume of oxygen gas is needed for the complete combustion of 4 liters of propane gas, blah, 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 blah. So they're already talking about a chemical reaction going on, and they're asking me math questions around a chemical reaction problem. So I first have to put down the chemical reaction, or else it is no good for me. Well, what are they doing here? Oxygen gas is needed to combust of propane gas. A combustion reaction. We are writing a combustion reaction, which means I take something with a bunch of C's and H's. It reacts with oxygen to always create carbon dioxide and water. So the guy that I'm combusting is the C3H8, that propane. So he is my first reactant, C3H8. I'm going to leave some space for the balancing. And to combust, we are always reacting with oxygen gas, which is important because that's what they're asking me to solve for. There's like something on my paper here, you guys. I have no clue. All right. And combustion reactions always produce CO2 and water. So that's a good review on combustion reactions. You always want to start off by balancing your carbons. So balancing my carbons, I have 3 here, so I need 3 over here, which means I put a 3 in front of CO2. Balance my hydrogens next. I got 8 over here, but only 2 over here. To get 8 over here, I need to put a 4 in front of H2O. And now I'm ready to balance my oxygens because there'd be a hot mess here because they're all over the place. So I go back and recount my oxygens on the product side. 3 times 2 gives me 6 oxygens from CO2. And then I have 4 oxygens from my H2O. 6 plus 4 is 10. That means I need 10 oxygens over on the reactant side. So to get 10, I put a 5 there. Okay, so I've done that. That is amazing. Now I'm ready to read the problem and see where are they giving me information and where are they asking me to solve for. So what volume of oxygen gas is needed for the complete combustion of 4 liters of propane gas and assume constant temperature and pressure. Okay. The number that they have provided me is a volume number. I zone in on that volume number because I'm like, oh my gosh, how exciting. So I have given you 4 liters of propane gas, and y'all are like, I do not know which one it is. And yes, I did tell you, but sometimes I won't tell you because I will assume that, this is oxygen, that's carbon dioxide, that's water, a process of elimination of sorts. So my given is 4.00 liters, right? And so my brain's already thinking, okay, volume of gas. Ooh, it totally matters what my temperature and pressure is. Let's see if the problem can help me out here. Oh, it says assume constant temperature and pressure. So we are at constant temperature and pressure, and I'm getting excited because I'm like, oh goodness, this is going to be real good for me. So we're going to write that at CTP. Ooh, okay. And what are they asking me to solve for? They're saying what volume, and volume is liters of who? Oxygen gas. So underneath my oxygen gas, I'm going to put a question mark, liters. And it can be redundant to write at STP again because it is all occurring under those constant temperatures and pressures. So looking at what I got going on here, guys, according to Avogadro, equal volumes have the same number of moles, which means the mole ratio is the volume ratio. I just get to use the coefficients for my balanced chemical equation, which states there are 5 oxygens, or 5 moles of oxygens for every 1 mole of propane. Or, now that we're at constant temperature and pressure, this also states there are 5 liters of oxygen for every 1 liter of propane. So I set up my Stoic. I get real excited because constant temperature and pressure means I got to do one thing and one thing only. Amazing. So I'm at 4.00 liters. I didn't give myself enough space, but whatever. C3H8. My volume ratio is my mole ratio, which will state there's 1 liter of C3H8 for every 5 liters of O2. So these numbers totally came from my balanced chemical equation. So volume ratio after being at CTP. So those now cancel off, liters of propane over liters of propane, which means my answer will allow me to solve for liters of oxygen gas because these are at constant temperature and pressure. Okay, so I'm taking 4 times 5. I don't need my calculator, but I'm going to use my calculator anyway because it's my security blanket. I like it. So 4 times 5 is 20. I know it is like 20 and you're like, amazing, walk away, but the sig figs do matter here, right? Our givens value of 4.00 tells me there are 3 sig figs. So in order for this to be, not 1 sig fig like 20 is currently written here, I've got to now not only put a decimal, but also put a 0 following that decimal. So that will give me 1, 2, 3 sig figs. And the units are liters of oxygen. Cool. So this is us now using under constant temperature and pressure, those mole ratios are also a volume ratio, which is really exciting. So what we've done so far is we've really focused in on solving stoichiometry gas problems that are dealing with stuff at STP or at CTP, which means you get to do some real cute, easy, shortcutting step. Let's see what happens maybe if we're not at standard or constant temperature and pressure values. So the next one says, first of all, you guys, oh my gosh, I need to balance this chemical equation. Words, we will get back to you. This one's a trickier one to balance. So for the sake of time and for your brain power to focus on one thing and only one thing today, we're going to go ahead and fill in the correct coefficients. You're welcome. Okay, so now we can read the problem. What mass of Fe2O3 is produced from 61.0 liters? Oh my gosh, you guys, my given. We know my given will either be a grams or a liters representation, right? Yes, right? So here my given is a liters of oxygen gas, right? So oxygen gas is right here. So I'm going to write that given 61.0 liters. And now since I know I'm starting at a volume, I'm like, okay, what is your temperature and pressure situation? Is it standard? Oh, where's my pressure? That don't look standard. I think standard pressure in ATM is 1. That's like 4.09. And my temperature, okay, well that is a temperature. Is it standard? No, if it was standard, it would be 0 degrees Celsius. Specifically for gas laws, we know we always use temperature in Kelvin. So actually, let's go ahead and blast out what that would be in Kelvin so we don't have to mess with that later. 147, to get it to Kelvin, we add 273 plus 273 equals, this is going to be 420 Kelvin. Good to know. So these two guys are not standard temperature and pressure, okay? It's also saying it's not at constant temperature and pressure. So we get to say not CTP or STP, okay? Ooh, which means, oh my gosh, you guys, then I do not get to use something super easy like a conversion factor of 22.4 or a volume or mole ratio. I gotta be dealing with this. We'll get there in a second. Let's figure out what it is they're trying to ask me to solve for. What mass of Fe2O3, there he is. So I'm solving for grams of this guy. So it looks like, since I'm starting with a volume not under constant or standard temperature and pressure conditions, I'm starting here, which means I'm going to use my ideal gas law, then I'm going to go to my mole ratio, and according where I wanted you to end at my grams, I'm going to go up to grams by using that molar mass. Okay, so I'm going to use the ideal gas law because we're not standard or constant. Okay, so what is the purpose of using the ideal gas law first? Well, you're going to rearrange the ideal gas law to solve for N, and that will be your given moles that you will plug into Stoic here in a second. But I still am going to use my green because this ideal gas law situation is for my given oxygen gas, okay? So I'm gonna just write the ideal gas law to see how see if we remember it. So PV equals nRT. If you want, you can rearrange that nice and pretty to make sure you know what things you're gonna have to plug in what order to solve for N. So rearrange to solve for N. This is going to be N is equal to PV over RT. Okay, so now I can grab a pressure. You're like, what pressure can I possibly grab? The one I gave you that you told me before that is not standard, right? Ooh, okay. My volume, what volume can I possibly plug in for? Well, the volume I gave you of 61 liters, right? R is the ideal gas law constant that will be provided for you. You will not find that information here in the problem. And then finally, temperature. What temperature I plug in? The one that I gave you that you said was not my standard or at constant. So now we are assembled all of the players. We are ready to go. We're going to plug in everything with our units. My pressure was 4.09 atm. My volume, where's my volume? 61.0 liters. Yes. My ideal gas law constant is 0.0821. And the units for that are liters atmospheres over moles Kelvin, right? And then finally, we got... what's our last guy? Our temperature, 420 Kelvin. Because if I am plugging stuff into the ideal gas law, my units for pressure have to be in atmospheres, my units for volume have to be in liters, and my units for temperature must be in Kelvin, or else I do not get to use that R constant. Okay, so I got to plug in, and this is going to give me my Gibbons moles, okay? Here we go. We go 4.09 times 61.0 equals, and I'm going to divide by 0.0821 and also divide by 420. Okay, so this is what I get. Now, the key here is that I'm not done getting to my final answer. My final answer is apparently to take it to grams of this guy over here. This is something I needed to do to get a little bit further in my mathematical calculation for this problem. So what I'm trying to say is that we're not going to want to round until the very, very, very end. You do not need to be writing that number down on your paper. There's a lot of numbers. You can totally chop that number off. You know, I think a good mentality would be to chop it off when you're writing it down at the number of sig figs that your final answer would be. Specifically, our final answer is going to be 3 sig figs because everything in this problem has 3 sig figs. So I'm actually going to write down here, this N is going to be equal to 7.24, and this is moles, right? But I'm going to keep this in my calculator and I'm going to grab it later when I have to use this to multiply to some more things here and later. That will give me a more precise answer at the very, very end. So now, you guys, I've gotten moles, and specifically this was moles of my given, my oxygen gas, right? So moles of my given, my oxygen gas. I now am ready to blast up here as something in my stoichiometry for my next step, okay? 7.24 moles, I'm not giving myself enough room, of O2. So y'all, we are here. We just had to use ideal gas law to get us to the moles, but we have made it. Now we are stoic like normal, mole ratio, molar mass, okay? So I'm at moles, we get excited. Moles, 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 we need to grab our coefficients. See, this is why I gave y'all wackadoo numbers. I was like, I want, you know, something fun besides a boring mole ratio of like 1s and 2s and stuff. Okay, according to this, there are 11 moles of O2 for every 4 moles of Fe3O2. The purpose of this step is to cancel off moles of O2 on top and on bottom, which means now I'm at moles of my ending, my Fe3O2, right? Well, here's the deal. So I got to take it to grams. We've done this before. We're going to use the molar mass, which states that for every 1 mole of Fe3O2, I have a certain amount of grams of Fe3O2, which means, oh my gosh, molar mass time, you guys. Finding the molar mass of Fe3O2 is I'm going to... Why do I keep writing? Oh my gosh. You guys, you know what I've done wrong? I have messed up where I'm going to. You guys, it asked me to go to Fe2O3. Well, that is not the correct car now, is it? Granted, it does not mess up anything that I've written down besides my last pink part of my problem. But guys, I'm going over here. Oh my gosh, that's the importance of reading the problem, which does affect my mole ratio, right? I'm not doing an 11:4 ratio. I'm doing an 11:2 ratio, okay? So make sure you're reading the problem and checking yourself. And the reason why I caught myself is I recognized that things were not matching up of what I was writing down here and what I was representing up here. Okay, so this is all good so far. So to find the molar mass of Fe3O2 is I would add 3 irons and 2 oxygens from my periodic table to get 159.7. Okay. The purpose of that is to cross off moles on top and on bottom, and the only remaining thing I have left is grams of that ending substance. So I've kept that mole value of oxygen that we solved for in my calculator, because now all I have to do is just take that same number that's stuck in my calculator and multiply it by whatever I need to and divide it by whatever I need to give me a more accurate answer. So I'm going to say that number of moles times 2 times 159.7 equals divided by 11, yes, and this is my answer. My answer, we said, is going to be rounded to 3 sig figs, so the numbers in my problem are all 3 sig figs. So my final answer is going to be 210, and that decimal is important to make that last 0 significant, and the units are the only thing I have not canceled off, grams of Fe3O2. Awesome. Okay, so we did our first one where I wasn't at standard temperature or at constant standard temperature and pressure or constant temperature and pressure. I gave you other temperature and pressure values to where if you see this, you're like ideal gas law, okay? So we used our ideal gas law for our given to figure out how many moles of our given we had, and then we stoiched like normal. Just made a little bit of a stumbling block, but that is okay. All the more reason for us to check our work and to just prove to you guys we're not all perfect, me included. Okay. Let's do our very last problem, see what our last problem's going on here. Blah, 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 words. Let's balance this guy. And I'm going to go real quick through the balancing of this guy because it's a tricky one. So just roll with me here. Okay, now we're going to get to the things. What did they give me? They gave me, grams. They gave me 0.0500 grams of boron hydride, that guy right there, okay? So I'm going to say I have 0.0500 grams of this guy. So it looks like I'm starting at grams, yeah? And they're asking me what will be the volume of gaseous water. So I'm solving for liters of water. So where's gaseous water in here? There he is, question mark liters. And if you are solving for volume, what is my temperature and pressure situation? Uh-oh, that's not standard. Oh no, right? So we're gonna say not CTP or STP, which my brain goes, okay, good, ideal gas law. But I'm not gonna use the ideal gas law yet. I'll be using the ideal gas law at the end of my problem when it comes to giving me that value. So it looks like I'm going from grams, 2 liters of a gas, not under constant or standard condition. So I'm going to go this with my molar mass and then my mole ratio, and then I'm going to take that moles that I solved for from my mole ratio step and plug that into the ideal gas law to solve for the volume. Okay, so let's go. I'm going to set up stoichiometry because I got to do stoichiometry first. Grams, it's like, yep, got to stoic to that. So I'm going to start with my 0.500 grams, never given myself enough space. When will I learn? B4H10. Well, if I got grams of B4H10 up here, I got to have grams of B4H10 down here, which means, periodic table is going to help me out, right? It'll state there's a certain amount of grams for every 1 mole of that same substance. Noticing I'm still keeping my colors green. I'm still talking about my beginning substance. So according to the periodic table, those 4 borons and 10 hydrogens are going to give him a molar mass of 53.34. All right, I'm at moles of my given. I get excited because it is mole ratio time, which means I'm going to look at the coefficients that I need. There is a 2 moles for every 10 moles ratio between boron hydride and water. So I'm going to write the 2 moles of boron hydride on the bottom, and then the 10 moles of, where am I going to? I'm not going to make another mistake. I'm on high alert now. I'm trying not to make any mistakes, hopefully. Okay, I done it that way because I want to cancel off like units on top and on bottom. So I have made it to end moles. Do not get excited and start stoichiometry to places that you are not being asked to go. I'm taking it to liters, but red flag, not. That means stop here. We're going to pull that guy out, and we are going to put that into the ideal gas law, whatever we get from this calculation, right? Okay, so I'm going to stop. I'm going to solve for moles. We're excited about that. We go 0.05 times 10 equals that, divided by 53.34 equals that, also divided by 2. Okay, so that's the number of moles of my water that I have. Congratulations. Now I'm going to write this down just so I can visually see it and plug that into my ideal gas law as showing a substitution step, right? And it's going to be rounded eventually to 3 sig figs, so I will only represent 3 sig figs of this value. But yes, this is moles of water. But the mentality of keeping your value in your calculator so eventually you can get the more accurate answer by not doing any short rounding on the in-between steps is still going to be important for us. So I'm going to take that value and I'm going to plug that in as N, okay? So I have, what's my ideal gas law? PV equals nRT. The point of this is I'm going to be solving for my volume. We wanted to get to liters. Well, here we are. We're going to be using the PV equals nRT to solve for V, okay? But that moles here is going to be plugged in here. I'm going to rearrange my equation to make it state volume is equal to. So volume is going to be equal to nRT over P, right? And this moles value is going to be plugged in as N. All right, so substituting my N value, which I've written it down short or rounded, but it's still in my calculator unrounded. And then I have a R value for the ideal gas law is 0.0821, and I'm running out of space. That is okay. Last thing I have to multiply up there is my temperature. Oh, my temperature better be in Kelvin. Is it in Kelvin? It is not. I've got to turn that degrees Celsius into Kelvin, right? So we will say T is equal to 30 plus a 273 will be 303 Kelvin. I should have done that, you guys. Right, so this is my temperature. And this is my pressure that we identified as not being standard or at constant, right? So then we're going to multiply 303 Kelvin. So all of this, we're going to then finally divide by my pressure. Hopefully my pressure is in ATM. If it's going into this ideal gas law, it is, thank goodness. So my pressure in atmospheres is 0.0274 ATM. Okay, so looking at what we've done so far is we pulled that moles of our ending out of our stoichiometry and we put it into the ideal gas law. This is going to allow for us to solve for volume. I'm having to write all over the place. It is not a big deal. Look at that, you guys. My moles, it's still in there, right? So now I'm just ready to say that times everything else that I need to multiply it by and then divide it by that pressure, which is exciting. So I say times 0.0821 times 303. And then I'm going to divide by that pressure, 0.0274, and this will give me the volume. If a volume is coming out of the ideal gas law, it will be a volume in liters, right? I will be rounding this answer to 3 sig figs because every other number in my problem has 3 sig figs. So my volume is going to be 4.26, and the units for this are liters, and of which thing specifically, it's going to be the water. The gaseous water. Yeah. Okay, so I'm actually going to zoom out a little bit so we can kind of see big picture some of the new stuff that we did here. We were able to handle the constant temperature and pressure and standard temperature and pressure because that's all strictly stoichiometry and sometimes using that mole ratio as a volume ratio, right? If I'm going from STP to CTP or STP to STP or CTP to CPT. But these last two problems that we worked together where I gave you temperatures and pressures that were not standard, or I'm asking you to solve for the ending substance at a temperature and pressure that's not standard. So I needed to use the ideal gas law. If I needed to use the ideal gas law first, I solved for N and I plugged that in and then put it in as my plug that in and put it in. After I solved for N, I then slammed that into stoichiometry to represent my givens moles and then continued on like normal like I did here to solve for whatever you need to solve. If I needed you to solve for a volume not under standard or constant temperature and pressure, that is a final step. But you do need to remember that when you get 2 moles of your given, you stop there and that will be your N that is in the ideal gas law, allowing you to solve for volume. So we've added some new fun things here with our stoichiometry abilities, and that makes me really, really excited. There will be more to come with this stoichiometry journey. It is not quite done yet, but this is a wonderful, cool thing that we can use the ideal gas law to help us calculate quantities of different substances in a chemical reaction when the conditions of temperature and pressure are not standard.